Good afternoon everyone. Today we will continue a course Applied Geomechanics for Geologists and we'll speak about strength properties. This is lecture plan for today. The first topic is Applied Strength Properties. The mechanical earth model is a description of mechanical facies, mechanical properties, stress and pore pressure and the function of that. Mechanical properties applied for drilling, completion, reservoir management. They are essential to estimate in situ stresses and conduct geomechanical analysis, including borehole stability analysis, sand production prediction, hydraulic fracturing, design, fault stability, and other geomechanical applications. More. This is one of example of application of mechanical earth model for borehole stability. When the hoop of circumferential stresses in a rock exceed the strength of rock, the rock would failure inside of tensile or shear fractures. Consequently, correct knowledge of strength and stress will allow select necessary mud weight and avoid big amount of shear and tensile fractures and events that associate with them. Here are breakouts, sticking, spools, landing that presented on this slide. One of part of mechanical earth model are mechanical facies. They allow divide into the cross section in rocks that have similar mechanical properties and behavior under pressure temperature condition. Mechanical facies used in BHA, casing depth optimization, hydraulic fracturing design, and discrete fracture net modeling. On this slide, you can see the example of definition of mechanical facies, sands and clays through rock properties with the stress profile. Also, the important application of mechanical facies is the unconventional reservoirs. Here you see the clustering of Bajenov unconventional formation on mechanical facies. This is very good property contrast between them. Okay, so we'll discuss it in full in one of future lectures. On this slide you see the example of mechanical facies clustering on any level. From core level, logging level to seismic level. Okay, the next part of lecture is core measurements for strength properties. This is a three base failure mechanism. At first is tensile failure, shear failure, and compaction or pore collapse. The tensile failure occurs when the effective tensile stress across the plane exceeds a critical value. This value is called tensile stress and given a symbol TSTR of T0. Tensile strength is one of the mechanical properties in the rock, and tensile zero mass clastic rocks is quite low, usually a few MPa or less. In some applications, zero tensile strength is a standard approximation, but in some cases TSTR can reach 10, 20 or 30 megapascals. Second, shear failure occurs when the shear stress along a certain plane of the specimen is sufficiently high. Eventually, a fractured zone is formed along the fracture plane, and both sides of the fracture plane more relative to each other due to friction, as you can see here on this slide. And at last, pore collapse is a reduction of a rock volume due to increase in a pore volume. And for example, this is chalk deposits in Ekofisk field in North Sea. The importance of compaction as well as shear and tensile failure bring focus on cap plasticity model. In this case, pore collapse occurs at high mean stress and low deviatoric stress, whereas a brittle shear failure occurs at low mean stress and high deviatoric stress. So the laboratory core testing provides the evidence of this behavior. Experiments also show that rock volume decrease with volumetric load lead to material stiffness increase. For pore compaction, the poroelastic plastic deformation cap model must be applied. But we will discuss the failure criteria in next lectures. You see here different types of laboratory tests that can be used and obtain strength properties. Figure shows 6 typical laboratory tests, more important laboratory tests, and let's discuss it below. At first is an axial compression strength test, also called as UCS, when the cylindric rock specimen is only compressed in the axial direction by axial load. Secondly, this is an axial strain test, UST, when the cylindrical rock specimen is only loaded in the axial direction and there is no lateral displacement. Tensile strength test, TSTR, when the cylindrical rock specimen is applied tensional force in axial direction. Number 4 is hydrostatic test, HST. If the cylindrical specimen also compressed with the same stress in all direction. 5 test is triaxial compressive test, TSS or MTCS multi-stage triaxial compressive strength. In this test, the rock specimen that have cylindrical form is compressed in both axial and lateral directions. The axial stress, also called sigma 1, is greater than the lateral stress, sigma 3, that equals sigma 2. This is confining stress. At last, this is polyaxial or a true triaxial compressive test. In this test, 3 independent and mutually perpendicular stress S1, S2 and S3 load to the faces in a rectangular prismatic specimen. As I showed before in previous lecture, this is one of laboratory equipment for mechanical properties core studies that we used in our work. In this slide you can see results of UCS and TSTR. As a result of UCS and axial compressive strength, the rock specimen compressed only in axial direction, and UCS is the relation of crushing force to sectional area of rock specimen. As for TSTR, tensile strength, the most common technique for rocks is the indirect approach known as a Brazilian tension test. We will return to it information later. This is typical stress strain diagram and a video of process unconfined compressive strength test. In the typical stress strain diagram, you see the experimental 5-stage that Rockefeller provides. At first it existed natural fracture closure stage, elastic deformation stage, fracture stable growth stage, fracture unstable growth stage, and post-peak stage. This is defining of static elastic properties on typical stress strain chart, and we'll discuss it in previous lecture. As I said before, the most popular and direct technique for TSTR is Brazilian test. In this technique, the rock sample is also cut into circular rod shape, but it's loaded from its side by a compressive force. When loading of a rock specimen between two plates, the rock becomes elliptical, and because of this, tensile stress arises at a middle of all rocks. So the rock will eventually failure into or more pieces at failure. This is example of a Brazilian indirect stress method. You can see here in this video as by increasing of loading, their rock sample failures. Okay, this is main X of failure after force application. Okay. This is main important that strain depends on confined pressure. For the time being, we will restrict discussion of rock stress to triaxial compressive tests with non-zero pore pressure with effective stresses. It's universally observed in such tests that sample strength is seen to increase monotonically with effective confining pressure. Because of strength depends on confining pressure, it's common to present strength test results use so-called Mohr circles or Mohr failure envelopes. The base for the Mohr circle is the estimation of shear stress and effective normal stress by graphically. So the equations for circles you can see under figures on this slide. Their y-axis is shear stress and x-axis is normal stress, effective normal stress. This slide shows 4 types of tests to determine the strengths of rocks. Test A is a uniaxial compressive strength discussed earlier. Test B is a one-stage triaxial stress test in which the sample failures during one stage. And at the stage of elastic deformation, elastic properties are measured. Test C is a multi-stage test at constant confining pressure in which, as a rule, the elastic properties are determined in elastic stage at last stage. Thus, the sample is repeatedly compressed and decompressed at the same confining pressure. Test D is a multi-stage test at different confining pressure. And this test allows you build a Mohr failure envelope with only one sample for triaxial compression and different confining pressure points. When performing triaxial test, it's necessary to remember that before each test it's necessary to calibrate the LVDT strain sensor to avoid errors The most suitable standard sample are plexiglass, bronze, aluminum and steel. Accordingly, if you correctly obtained reference value of elastic properties on test sample, then in the future the sensor can be used for subsequent work. In this case, you can see the result for Mohr failure envelope that includes 3 circles. First is TSTR, second in UCS, and third is one-stage TCS. In this case, you can see the result of Mohr failure envelope for 5 circles. First circle is TSTR, second also UCS, and all another circles are MTCS test with difference confining pressure. This is example of construction of a Mohr failure envelope that includes 5 circles. The first circle is TSTR. Second circle is UCS. Third circle and or another circles are yield values from MTCS with different confining pressure. And this is approximated Mohr envelope failure with equation that you can see on the chart. And consequently, the result parameters of Mohr envelope, the cohesion strength and friction angle, you can see above the chart. According to John, the rock can be classified according to their UCS. The first group of rocks is extremely weak rocks. Their UCS from 0.25 to 1 megapascal. The second group is very weak rocks from 1 to 5 megapascal. Weak rocks from 5 to 25 megapascal. They include as rock as chalk. Medium strong rocks includes clay stones, coals, concretes, schist, shale, siltstone. Their UCS include from 25 to 50 megapascal. Strong rock are limestone, marbles, fillets, sandstones, shales, schists. UCS is from 50 to 100 megapascal. Very strong rock, common magmatic rock. They are amphibolites, metamorphized sandstones, basalt, gabbros, gneiss, granodiorite, etc. UCS from 100 to 250 megapascal. And at last, extremely strong includes fresh basalt, chert, diabase, gneisses, granite and quartzite. The UCS more 250 megapascals. In general, rocks or rock masses always present certain degree and anisotropy. Particular in fractured rock masses or slates, shale and schists. Ambrose et al. Authors extensively studied the strong influence of planar anisotropy on strong grain. This figure schematically shows his experimental methods and their observed results. The graph on left part of slide shows the failure stress as called as sigma 1 as a function of angle for a different confining pressure. Color points represent sigma 3 from 0 to 10 megapascal. Here, beta angle is the angle between the maximum stress and the orientation of weak planes or bedding planes. As can be seen in this figure, the compressive strength of the anisotropic rocks is the lowest at around beta angle near 60 degrees. The next unit of lecture is strength properties prediction methods. There are a number of published log curve strength correlation that can be used for rock strength modeling. Thus, empirical correlation and relationships are developed for specific rock types, depth range and field. The general application therefore need to be critically assessed on case by case. Okay, this is example of UCS profile for 12 wells. This is clastic rocks. They include as mechanical facies as sandstone and shales. You can see here good correlation between logs and curve. Another example of TSTR distribution by 12 wells. This is same cross section than you saw at the previous slide. This is Haxar's FANG table equation from literature source. This is not big table, but the table includes almost famous relationship for FANG calculation. One of the well-known FANG equation from literature, this is plumb correlation that shows that the friction angle decreases with decreasing volume fraction of grains. In other words, the sandstones have more friction angle than clays. On this picture, you may see the distribution of friction angle on wells for the same cross section that I showed you in previous slides. On this slide represented example of combined properties. The combined properties includes gamma ray, caliper, density, slowness of P and S wave, Poisson ratio dynamic, Young model static and dynamic, friction angle and unconfined compressive strength. This is another example of combined properties that calibrated of core data. One of important method for determining UCS is the EST indicator. It's measured during the drilling process and calculated from parameters such as string rotational torque, beat depth, and string rotational speed. The equation for calculation of indicator of stress EST or equivalent strength is on this slide. The next unit, this is the strength properties calculation in LithoStudio software. You may see on this slide links for detailed analysis of strength properties calculation in LithoStudio in our YouTube channel. This is a reference that I will recommend you to study this topic. This presentation made with Slides Go. Thank you, Slides Go. Thank you so much.